Good morning. Welcome in our Cerium Design Virtual Conference, Session A of Mechanical and Aerospace Engineering. My name is Dan Kujawski, and I will host this morning session. So after the presentation, there will be question and answer session, and you can ask the question by unmuting your mic or just typing your question in chat room. So team, the virtual floor, it's yours, but I only see one presenter on the screen. So can we have others camera on as well?
Yeah, that should be on for you.
We have the second one, and we need one more.
Yeah, it should be on there.
Yeah, all three of us are here.
Thank you very much. So the virtual floor is yours. You can start.
All right. Hello, everyone. My name is Craig Zemer, and along with my partners, Jacob Perry and Ray Vigo, we will be presenting our senior design project, which focuses on the reduction of aeroacoustic noise generated by wind turbine blades. Our agenda today will include a brief introduction of our project, followed by the design alternatives for reducing noise. Then we will dive into the simulation, experiment, and results.
To begin, we will discuss why we're focusing on this issue, where the sound is coming from, and the objectives for this project. Wind turbines have been around for a long time, and they're getting more attention as the world begins to focus on renewable energy sources. As great as they are for the environment, they have a few aesthetic and practical drawbacks. Wind turbines are very noisy. The large blades produce a significant amount of aerodynamically generated noise. This is the reason you don't see these guys in the city. They are usually placed out in the rural areas and even in the ocean so that they don't bother anyone nearby. Unfortunately, this limits the expansion of this renewable energy source, and not only are they annoying, but they can potentially be dangerous. The noise generated in the infrasound region, which is 0 to 20 hertz, can cause sleep disturbance and psychological stress. Therefore, the focus of our research will be in this frequency range. Aeroacoustic noise itself is a product of vortices generated from the trailing edge of an airfoil. This is known as self-noise. When an airfoil is in laminar flow, the air becomes turbulent in the separation region. This is on the upper surface closer to the trailing edge. The air begins to roll up and separate, which forms these vortices. As they shed, they produce pressure fluctuations in the air. When the air fluctuates, transverse waves are formed. This is perceived as noise to humans.
This is an illustration of one of our airfoils, the baseline. You can see the correlation between turbulent air in the picture above and the acoustic power level that's generated in the picture below. As you can see from these two, they're pretty similar, so that's why we're focusing on turbulent air. And as far as the objectives for our specific project, we want to reduce the acoustic power from our baseline, which is the NACA 64-618 airfoil profile. We want to correlate our simulation and experimental values, and we'll do this with a coefficient that we defined. And overall, we want to develop a comprehensive research process for future students.
We'll now go over the design alternatives for this project. These are also referred to as NRFs, or noise reducing features. All the alternative designs that will be outlined in the next few slides were modeled from the geometry of the baseline model. The National Renewable Energy Laboratory has developed a 5 megawatt offshore turbine that has an easily obtainable set of turbine blade profiles. Since the full blade is not a practical length to experiment on, a smaller section was taken near the tip that uses the profile of a NACA 64-618, which is at the location of about point D on the picture.
So for modeling, we used SOLIDWORKS 2019, and we scaled down our airfoil to a 4-inch chord and width. And all the alterations were made to this baseline. As you can see in the bottom left corner, just some holes for one of our designs is going right through the trailing edge. And we're also able to incorporate a couple holes for mounting our magnets on the bottom of the airfoil.
Now we'll talk about the chosen design alternatives that were developed. The first is the serrated trailing edge. The jagged ends alter the pressure distribution between the upper and lower surfaces before they reach the tip. The dimensions of the serration are outlined in the table with the handy image above it describing how the dimensions were applied. The next alternative was based on the wing of an owl. Owls fly silently, so we wanted to mimic some of the characteristics of their wing geometry. The feathers of an owl have tiny little hairs that act as a canopy for air to flow through, reducing some of the boundary layer separation because there is more surface area for the air to come into contact with. This is mimicked by vertical fins on each of the cone-like fingers at the trailing edge. The cone fingers are based on the fringes located on the end of the wing of the owl and share a similar purpose to the serrated design.
So this is our hole mesh design, which is inspired by porous materials. Since we are 3D printing, we were able to just incorporate the holes straight into the body. These holes are focused on the separation layer. That's the reason for them being towards the trailing edge on the upper surface. And the purpose is to disrupt the roll-up characteristics of air as it begins to separate and become turbulent. And it also directs the air downwards towards the lower surface. We have a couple different versions of this airfoil, one with more holes, so simulating a finer porosity, and one with a few less, so less porosity.
We also tried to implement a porous trailing edge. The purpose behind this model was to utilize a rigid porous material on the trailing edge to reduce air disturbance, and pumice was selected as it's easy to model, it's rigid, and it's also porous. The purpose is to allow the airflow to flow from the high pressure side to the low pressure side through the material.
And finally, we have a feathered trailing edge, which is directly inspired by nature or an actual bird. And these feathers were inset into the airfoil body itself. And the intention is to, again, disrupt some of the roll-up characteristics and also produce irregular pressure fluctuations, as well as redirect the vortex shedding so it's not all in one direction.
Next, we're going to go over the simulation and experimentation. That includes our manufacturing process, the testing procedure, microphone placement, data processing, and the simulation. All the models were printed together on a Stratus F370 industrial 3D printer. This printer is capable of printing a layer thickness of 1/100th of an inch with a tolerance of 8/1000th of an inch. They were printed in PLA material with an ABS support material. The models were printed vertically on the print bed to allow for a smoother airfoil surface, and the holes were printed on the bottom surface to insert magnets used to hold the models on the test stand.
For our testing procedure, we did the tests at the Fluids Laboratory in Western's Parkview campus. They have an acoustic chamber with a wind tunnel there. The airfoils were set right in front of the airflow. The speed was set at 30 miles an hour to simulate practical speeds for a wind turbine blade. And we had 4 different microphone placements to capture the sound, which were recorded, and the data was analyzed in MATLAB.
The placements of the microphones were determined by a preliminary simulation. Based on that simulation, a distance of 1 inch from the trailing edge and the horizontal plane was chosen. The vertical placements were located in line with the tip, as well as 1/2 inch above the tip to pick up on any shedding vortices. Out of the 2 microphone channels that we used in the experiment, we only ended up analyzing the data for one on channel 1. The channel 2 ended up having locations too far below the trailing edge tip. That wasn't really the focus of our project. The channel 1 microphone was placed in 4 different positions, 2 directly behind the midplane of the trailing edge and 2 off in the side plane. The first test was 1/2 inch above the trailing edge, the second aligned with the tip of the trailing edge, and then tests 3 and 4 followed that same pattern but off to the side. The data was exported from the acoustic software into a couple of different file types. The frequency plots, as seen on the top, were pasted into a Word document, and then the raw numerical data was exported into separate Excel spreadsheets for each test. The next step was to reorganize the workbook so that there was a single file to import from rather than 4. The concentrated workbook consisted of 8 sheets, 1 for the background, 1 for the baseline, and then the other 6 for the NRF designs. With all the numerical data into one file, we could easily import the data into MATLAB for processing. Out of the 2000 hertz range that was assumed, or that was measured, we only focused on the infrasound that was in the 0 to 20 hertz range. The resulting reduced data resembles a less messy plot, like the plot of the background noise for test 3 shown here. The background noise for each of the tests was then taken and subtracted from each of the airfoils to remove any interfering ambient sounds. These two plots show before and after of the background removal for test number 3 on all the airfoils. As you can see, there's a high concentration of noise below 0 decibels. This implies that the airfoil was quieter than the background, but we believe this is somehow a result of the nature of how the experiment was conducted and the error that can accumulate over time if not careful.
So in addition to our physical experiments, we simulated all the airfoils, most of the airfoils in ANSYS Fluent. A lot of them were too complex, such as the porous trailing edge and the feathers, and the owl trailing edge couldn't be simulated, but the baseline, the serrated edge, and the whole mesh airfoils were able to be simulated in ANSYS. Off to the left, you can see the fluid boundary for our simulations, which was intended to reflect our actual experiments, so about 3 inches from the inlet. And all the mesh was refined and biased towards the airfoil, so it was more accurate in the desired regions. For the simulation itself, we use the SST K Omega model as our turbulent model. This is a good model for boundary layer flows, as well as using minimal computational power. We use the broadband acoustic model, which shows the propagation of noise off the airfoil without any background noise. We used a pretty small reference acoustic power since we were in a quiet room, in a quiet chamber. We had 1,000 iterations to ensure a converging solution, and the speed was set to 10 meters a second, which is around 30 miles an hour, so it resembles our tests. These color contours were developed, as you can see on the bottom. This is a color contour for velocity. So warmer colors mean a higher velocity, cooler colors are a lower velocity. So this is an example of what that would look like for air velocity. But for us, we are more focused on the acoustic noise itself. So these are the acoustic noise levels, power levels for our fine hole mesh. And you can see we have 2 different ones. On the top, there's the right side contour. Since we had a couple tests, our microphones were off to the side. And then we had one on the mid plane, which went right across the holes. As you can see, it's a little bit louder as they go across the holes, but a little farther back, it does get quieter. And we had 2 planes because a lot of our designs were 3D, such as holes, serrations, fins, stuff like that. So we needed to take data points in multiple planes.
Now we'll go through the results of our experiment. The results of the experiment give us a good set of data to analyze. The full range that was measured was from 0 to 2000 hertz. The full spectrum of noise for the baseline can be seen in these plots for each of the tests. The channel we chose to focus on is in blue. The noise data was also analyzed in the narrow infrasound frequency range to gauge whether the NRFs were effective at reducing noise. It's important to also consider how the overall noise was affected in the broader range of frequencies. Frequency range of 0 to 1000 hertz was picked as an expanded low frequency range. As you can see from this plot, the lines start to get a little messy, so it was necessary to look at a simplified numerical method instead. To better understand the effects that the alternatives had in comparison with the baseline, a single value of an average difference was calculated. We call this the differential noise level, or DNL. For each of the data points in a range, the baseline noise level is subtracted from the NRF data to give a change in noise levels. A positive number implies an increase in noise over the baseline, while a negative number is a decrease in noise. The DNL data for each test and range of the frequencies are shown here in the tables. These are the average differences in noise, so it's okay to have a negative number. In fact, that's what we're aiming for. The significant total is the sum of the 2 tests that we deemed a more accurate representation, which would be tests 3 and 4. Tests 1 and 2 were directly in the airflow stream, so there's possibility of interference with the air there. The DNL data was plotted on a bar graph to visualize the changes. The ones on the left are the infrasound range, and the ones on the right are the expanded low frequency range.
So through our overall analysis compared to our objectives, we can see that the most significant reduction in noise was produced by the fine hole mesh design. As you can see in this table on the bottom, these are our DNLs right here, and the finer hole mesh did have the most significant noise reduction out of all the design alternatives we had. As part of our objective, we want to correlate the simulated and experimental values. So through analysis, we do that with a defined coefficient known as the OCAT coefficient. So this OCAT coefficient is taken from our simulated and experimental values. It's a sum of the experimental value acoustic power over the simulated acoustic power, and it's an average for all 4 tests. And we do this for the baseline to develop an empirical model for the rest of the simulation so that we have a more accurate prediction for successive tests. As you can see, our OCAT coefficient for the baseline was 0.1374, and this was applied to all our other simulated values for the other airfoils. And this is a lot easier to see on a graph. So all the dark brown lines for each of these charts represents the simulated values for acoustic power level for each test, 1, 2, 3, and 4. And the gold plot line is the actual experimentation value for those same tests. As you can see, the trends are very similar. The peaks are in the same place for test 2 and 4. So they do look good, but they are fairly different. So with the OCAT coefficient, this prediction is a little more accurate as represented by the gray line here. You see that for test 2 and test 1, they are pretty close, very close, rather than the simulation values. And as Craig described, tests 3 and 4 did have some negative values with some error, but the results are still very close with the OCAT coefficient.
4 criteria were considered and weighted in order of importance for the scope of the project. Each of the airfoils were given a score of ±5 in each of the categories relative to how they compared to the baseline. They were scored on how easy and practical it is to simulate the airfoil. Is it difficult or easy to manufacture them? Their overall contribution to reducing noise over a wide frequency, and their contribution to reducing noise in the infrasound range. The noise contribution scores were weighted using the results of the DNL values.
So our overall conclusions with our objectives to reduce the noise off of the NACA 64-618 profile, the whole mesh design was the most successful alternative in doing so, decreasing that aerodynamically generated noise. Overall, we did develop a very comprehensive research process for future students, all the way from modeling them in SolidWorks to getting them printed and finally testing them. Other students can use the project that we've developed, look through our report, look through this presentation, and we'll be able to jump right in and have a good start on that. And for correlating our experimental and simulated values, we developed that coefficient so that the simulated values would offer a more accurate prediction.
Lastly, we have some recommendations for future groups that decide to follow the same subject. For one, the airfoil stand was very flimsy, and the small piece that held on the airfoils was also very flimsy. This can be improved on for a sturdier design. Adding a larger array of microphones could better allow the rate of noise propagation in the longitudinal direction to be collected. The model print quality can be improved on, as 3D printing often results in some surface roughness. Smoother surfaces would result in less surface drag and improve the results. Lastly, utilizing the Fox, William, and Hawking acoustic model and ANSYS can increase the accuracy of the simulations. Overall, future research should focus on the reduction of the OCAT coefficient and yield more consistent trends.
Finally, we want to say thanks to these people. We want to say thanks to our faculty advisor, Dr. Baid Shrestha, for helping us out in this research process, to Hussein Mohammed for helping us actually take the data from the microphones and record our airfoils, Ibrahim Uves from ANSYS for helping us develop the simulation, Kevin Bancroft from ORCID for printing our models, Steve Perry for purchasing the magnets that were used for mounting, Trenton Holman, who actually developed the wind tunnel in the senior design project, for helping us out in our preliminary research. And we want to thank Western Michigan University for facilitating and providing the resources for this project. So, are there any questions?
Thank you. The presentation is open for comments or questions.
I had some questions, I suppose.
Sure.
First of all, would you mind going back to slide number 7, please?
Yeah, let me share that again real quick. Slide. You want 7?
Yeah, it should be back close to the beginning.
Holy schmoly. Okay.
Yeah, I counted about 45 slides, so.
Yeah, we got 41, I think. Ah, shoot. All right, there you go.
Okay. Okay. No, it's not this one. It's the one that had the A through E on it on the lower left side.
Slide 9.
Oh, sorry.
9.
the
Okay.
baseline one.
Sorry. Thank you. Yeah, that one. Would you guys mind explaining that, please? What exactly does that mean in terms of the shape of the airfoil with the placement along the wing fin?
Yeah, I got this one. So the wind turbine blades have multiple different airfoil profiles to them. Usually they're thicker in thickness at near the hub, and they get thinner as they go down. We had modeled a full length one with all the different air profiles, but since we found in our research that most of the noise comes from like near the tip of the blade, we focused on one of the later sections down the span.
Okay, thank you. And if I may ask another question, wouldn't some of the designs that you offered reduce the efficiency of the wings since there would be less air, and since there would be less wind resistance acting on the fin?
Yeah, so we weren't able to collect lift and drag data because of our test setup. The actual stand was kind of broken there, so we couldn't do that. But in the simulations, a few of them did offer similar lift and drag properties. So you can find that data in the simulations. So a few of them did decrease that coefficient a little bit, but a lot of them were similar. So that is definitely something to take into consideration for design.
All right. Why have these designs not been thought of or implemented before?
That goes back to our benchmarking. You know, it goes for simulating them, manufacturing them. These are pretty large structures, so if you were to stick a few holes in the back of them, they would be pretty flimsy, which you don't want. So that would take quite a bit more development. But simulation too does take a lot of time, especially for really complex features. So, you know, you want to obviously keep focusing on that, but there's quite a few factors that they're not being implemented in real life yet, but they are, you know, a huge point of research.
Okay. Last question. Isn't there a possibility of some of the fins breaking from high wind with the designs that you've suggested?
Yeah, so that could probably decrease the structural integrity. And again, that's going to have to go back to the design and testing of these airfoils at a larger scale. If they found one was significantly weaker, then obviously that design wouldn't be used. But I believe some of our designs would still maintain a pretty rigid structure, considering that the holes are at the end of the trailing edge, which is usually a thinner part. And a lot of that stress is going to be on the front of the blade. So,
Okay. Thank you.
Thank you. Any other questions to the team? We still have a lot of time. Maybe I can ask a question, or rather, I will ask for your comments. Your experiments were run in constant flow velocity, but in reality, wind is not constant. How this can change your approach to the project? Any comments?
I suppose for future recommendation, you could actually have someone adjusting the wind speed and see how the airfoil would react under changing wind velocities. That wasn't something we thought of at the time of testing, though.
Thank you.
There's the one question in the chat room. Can you answer that, guys?
It looks like that one was from the last group.
This is from the last group question.
No. Great work, guys. What was the most challenging part of the project for each of you, and how do you overcome it?
I would say for me, I did all the simulation, and I had never touched ANSYS before this project. And I'm also a mechanical student, so this is all aero stuff. So that was pretty interesting to learn something I had never learned, and all the acoustic stuff. So pretty much everything in this project I had never done or looked at before. So this whole project was quite a challenge, but it was really cool to learn.
A lot of the data processing in MATLAB I had never done before. And so learning how to import all the data in the Excel spreadsheet was quite new to me, and then having to parse through it to make all the plots as well.
Yeah, I think designing the airfoils and coordinating with the sponsor that we had that printed them, trying to figure out the best way to print the models. We worked a lot over a summer internship with the best way to print things and a lot of SolidWorks. So I think that was a really fun challenge to try and figure out and make sure the models turned out as good as they possibly could.
Thank you.
Thank you very much. Thank you for presenting team.
Could I ask the team a quick question? This is Steve Perry. Very proud to be able.
Go ahead. We lost you.
Hello, Steve. We lost you.
Very, very. Okay.
You're cutting in and out, Steve.
How about
You
now?
cut
How's
off.
that?
Let's see if we can hear from him again. There's some connection
How's
problem.
that, guys?
That's
That's a
better.
little better.
Is that a little better?
Yes, now it's okay.
Okay, so quick question. This 20 hertz range that you're looking at seems very low. Is that actually sentiments?
So it's called infrasound, which is pretty low on the actual hearing range, but on a bigger scale, especially, you know, it's one of those things like that you can feel. It's like the wub wub wub, kind of in that last picture, the little cartoon, but that's really where the infrasound is, that very low frequency. It is close to hearing, but it causes like more physical stuff like that you wouldn't exactly hear, but you might be able to feel.
Interesting. So it's almost a tactile feel.
Yeah.
When you were doing your testing, could you tell any differences subjectively, just listening in the lab as the air flew over?
No.
The fan was
Probably.
a little loud, so.
Yeah.
Probably not at this scale, but I'm sure if you were at a larger scale, you might actually be able to feel something.
Interesting. All right. Thanks, guys. Great project.
Yep. Thank you.
Thank you.
Thank you for your presentation, and thank you for audience for attending this presentation. And we will have another presentation at 10:30. Thank you very much.